Hi everyone. Welcome to 5th QWebinar of the QWorld. This time we will try a question-answer session first time, and we are very thankful to Scott Aaronson to accept our invitation. I think we don't need to introduce him. He's already maybe the most, maybe one of a few the most person in the quantum computing. His blog is already attract, I guess, kind of everyone interested in quantum computing. Today we are also having first time guest moderator, and I also would like to thank Andris Ambainis accepting to be one of the moderators today. I am also, thanks to him, I am kind of his group, like this is my 7th year, and I am still curious why he's still keeping me there, but yeah, thanks to him to be here. This will be our 5th webinar, and it will be only for question answer. Together with Agnieszka, we make this all organizational stuff together, and all these nice graphics you've seen, I guess, on the Twitter or Facebook, they're all prepared by Agnieszka, thanks to her, sorry. Also Zoltan from QWorld will be one of the moderators today. Andris is not directly under QWorld, but also I will also mention about his significant contribution to the QWorld very soon. But he's definitely the boss of the quantum in Latvia. So let me proceed. So I will shortly mention about the protocol, and then I will make a very short introduction about the QWorld, and then we will start our question answer session with Scott. So QWorld is quite careful about the codes. So we are here together to talk about quantum. So please, all of us should talk about the quantum, first of all, scientific way. And also we should be nice to each other, and any unpleasant situation, just report us, and we just maybe remove some people from the meeting. We are already recording this meeting, and it will be available on our YouTube channel later. And you shouldn't record or broadcast this meeting because we didn't ask any permission from the participants here. We have more than 200 registered people and more than 30 questions already. Also, our moderation prepared some questions, but you can still ask your questions by using commenting. Zoltan will follow the YouTube. You can use commenting there. And here I and Andris will follow the comments by the Zoom. You can still ask your questions, but our time is limited. We may not ask all the questions, and also our moderator can be more selective. Just be ready for this. So I will start again with the motto of QWorld. We started with this motto. We invite everyone to be part of the second quantum revolution. But of course, to make it more concrete, it's more about creating opportunities for every potentially interested person under the QWorld. Today, we will talk kind of history of the quantum computing. And this is why I start a short timeline about the QWorld, how it started, etc. So basically, it's, let's say, originated or started from Latvia in Andris group. So in end of August 2018, almost 2 years ago, I initiated the quantum software group, and in my mind, I didn't expect maybe to come until this point. Around October, when I checked this Qiskit, for example, and also checked this Jupyter notebooks, I just noticed by myself, these are very nice tools for education. And if you use them, for example, if you do some workshops, and we can really reach more and more people. And I immediately put this to action. And in a month, we organized our first 2-day long workshop on quantum computing and programming. We also organized it with local girl groups, Riga Tech Girls, and it was kind of only for the women. And we had 14 diploma receivers at that time. And then after a couple of weeks, we do the same for the high school students, the same workshop. And at the same time, we also had just formulated this idea of QDrive project. This project is implemented last summer when there was no COVID or something similar. So we were free to travel around to Europe. So this QDrive project takes almost 80 days, and we travel by a car. I had a team of 2 and 3 people, time to time. And we really organized 11 more workshops in 8 different countries, and we hand out more than 200 diplomas. And we also create some initiatives during this QDrive. And then at the end, we were kind of 5 Q cousins already: Latvia, Turkey, Hungary, Balkans, and Poland. Then we decided to just go to global level. And around November, we just make things more formal. We had our first website, like to explain us, and also we formed the first board. You see these 7 people. These 7 people are the founding boards of the QWorld. I am from Latvia, Maxim also from Latvia with Agnieszka. And from Poland, we have Adam and Pavel. From Turkey, we have Özlem. And also from Hungary, we have Zoltan. And until this time, Andris really supported us a lot. First of all, he was the boss of the Latvian team. Besides this, also he financially supported also all this QDrive. I mean, I also would like to thank to him in behalf of QWorld. I mean, maybe without his support, we may not come to until this point. And in November, we also got our first sponsorship. I also would like to mention about this Unitary Fund. Maybe some of you heard, some of you didn't heard, but they also really have a nice idea. They are giving like, let's say, micro grants to some software projects. And I guess they are already giving maybe more than 10 or 20. And they are also supporting to have a good open quantum ecosystem. So up to date, we organized 33 workshops, 1 hackathon altogether, all groups under QWorld. We hand out almost 700 diplomas. We are preparing new educational materials to do more workshops and hackathons. Also this summer, we are implementing our first internship program. We are also getting day-to-day more professional, let's say, also try to learn such things, and we are also reorganizing ourselves. Basically, we will have 2 big networks, quantum cousins that I already mentioned, and also we want to establish a women exclusive groups. We plan to do it in city-based, and we have a Q Academy under which we want to education. We have been active basically for education, but we also want to extend it for research, and we also have a special emphasis for the high school students. This is why we have a special department for Q Junior. Also, we understand that for better operation, we really some administration part, some marketing, and even some maybe finance people. We have a lot of ideas. We have a good roadmap, but we need more people. And currently, what we have is really kind of overloaded all of us. We are also kind of suffering of time, couldn't find enough time and energy. And we also invite everyone who can be interested in to join QWorld. The best way to join, maybe form a quantum cousin group, because once you have this group, then we can formally talk together, and then we can also individually join this Q Academy, for example, or you can help us in the operations. After QDrive, I thought we were 5 cousins. Now we are 7. Russia and Slovakia joined us. We expect Czech and Finland will also join us soon. We are also discussing, let's say, around 10 different countries, 10 groups from different countries. You see some of them here. Maybe I forgot that there could be a few more. And yeah, we hope to be bigger. The idea is working together, sharing and supporting each other, and then really just try to include everyone, every interested one to this quantum ecosystem. So this is a short timeline of the QWorld, and I would like once more thanks to Andris. supporting from the beginning all the ideas and also us, even financially and in other way. So now we will switch to question answer session. So basically we will use a Google form for this, and we will start with Andris, the first questions.
Okay.
So Scott,
yeah,
thanks for finding time to join us, and
well, thanks for having me.
Yeah, and well, first we'll have some questions from the organizers and the moderators. So,
okay, all right.
The first question about which we are wondering is, how did you decide to become a computer scientist, and how?
Okay.
Yeah.
And also quantum computing. Yeah. Well, so I think I got into computer science as an adolescent, mostly because I wanted to write my own video games. You know, I was very into Nintendo, and you know, each game just seemed like an entire universe in miniature. But unlike our universe, it was a universe that someone completely understood because they had created it. And I felt like, you know, I wanted to understand what was involved with that. And when someone showed me basic programming, I say that, like, for me, it was like learning where babies come from, right? It was a revelation. And, you know, and especially the fact that, you know, once you've learned one programming language, then you've basically learned them all, because, you know, any language can emulate any other one. As long as it, you know, it has some you know, a modest amount of expressive power, right? In other words, the Church-Turing thesis. I mean, that was utterly amazing to me. You know, as I got more into computer science, I found out that while I loved programming, I did not love, you know, having to document my code, having to make it work with other people's code, having to get it done by a deadline. And, you know, other people were just much better than I was at software development. And I got, you know, more and more drawn into the theoretical side of, I guess, because I liked math. And yeah, when I did work on, you know, for example, on RoboCup, on a robot soccer project when I was an undergraduate, you know, I was the one who would say, well, you know, the way you're trying to do this is, you know, I can prove that that the problem is NP complete, and the other people would be saying, well, you know, we don't care because we, you know, we've already moved on to a different way, right? And you know, so I realized that sort of my comparative advantage was maybe in theory. Now, as for quantum computing, you know, I would say that I first heard about it when I was 14 or 15, when I think I read a popular article about Shor's algorithm, which had just recently been discovered. And my first reaction was, this sounds like garbage. This sounds like physicists who are just making something up and do not understand the enormity of what they're up against, right? That, you know, the whole universe should basically be like a sort of giant video game, right? It should be, you know, some kind of cellular automaton with, you know, pixels that are, you know, getting updated, you know, based on what's happening to their neighbors, you know, by some simple computational rules. And so this whole business of trying all of the possible answers in parallel and so forth, you know, that just can't, it seems like it can't be right. But then, you know, a few years later, I was lucky enough to do a summer internship at Bell Labs, and it was just, you know, some software development. But my boss was nice enough to say, you know, I could spend a month reading about quantum computing because I was interested in it. So I read, you know, the paper by Bernstein and Vazirani, Quantum Complexity Theory. I read, you know, a lot of the other works that were just then coming out, and it started dawning on me, you know, quantum mechanics it seems like a real thing. You know, it is something of, you know, even of comparable enormity to the Church-Turing thesis, right? It is exactly the kind of thing that could enlarge, you know, our notion of what is computable in polynomial time. you know, and what I also discovered was that it was a lot more subtle than the popular articles would have led someone to believe, right? That it's not just a simple matter of trying all of the possible answers in parallel. You know, it's this much more interesting business where you have to choreograph a pattern of interference among all of these exponentially many different amplitudes, you know, and use the fact that they can be positive or negative, or, you know, they can be complex numbers, they can cancel each other out. And so it seemed to me like, you know, this is stranger than any science fiction writer would have had enough imagination to invent, right? Like it is strange. You know, I think Hardy said this about, you know, when he saw the letter from Ramanujan, right? He said, you know, like these formulas must be right, because if they weren't, then no one would have had the imagination to invent them. Right, you know, and I kind of felt that way, learning the model of quantum computation. Then I discovered that Lav Grover worked in the same building as I did at Bell Labs. So I sought him out. I told him some ideas that I had for improving Grover's algorithm, which were complete nonsense, did not work at all. But, you know, then Lav was kind enough to invite me back to do an internship with him the following summer. And now at that second internship, I met other students interested in quantum computing. Hein Rohrig was there, and then also Ashwin Nayak from Berkeley. And, you know, they told me about, you know, what were the current problems in quantum computing. I remember that I spent that whole summer trying to solve a problem in quantum computing, which was to show that quantum computers can only get a square root speed up over classical computers for evaluating and/or trees. Okay, for you know, in other words, like for evaluating game trees of a small depth. And you know, I spent the whole summer on it trying to use the polynomial method. I was not, which I had just, you know, been learning about. I was not able to do that. And then the following fall, Ashwin told me, listen, there's another student at Berkeley named Andris Ambainis, and he just solved that problem, you know, by inventing a completely new lower bound method. So I wrote to Andris, I got a hold of that paper, and I was completely blown away by it. And I felt like I have to go to Berkeley. I have to learn, you know, whatever these people, you know at Berkeley. You know, of course, you know, it's not as if going to Berkeley can magically make someone else into you, Andris, but that, you know, you actually had a huge influence on me at that time. It was, you know, I was lucky enough to be admitted to Berkeley for graduate school, but it was actually the machine learning people who recruited me there, Mike Jordan in particular. And so I did machine learning mostly my first year there, but by the end of the first year, I guess I had fallen in with Umesh's group. And, you know, by the way, Andris, I believe that was your last year there. So we did overlap for that year. So, and you know, I guess, you know, the field, I mean, by now I feel like this field has broadened to sort of anything at the intersection of physics and the theory of computation. And that's sort of, you know, that's a very large scope. And, you know, the field has continued to just throw up enough interesting stuff that, you know, anytime that I think of leaving, that there's just too much that's happening that's interesting that keeps me here.
Okay, so yeah, so the second thing about which we are wondering is, can you tell us what, in your opinion, is the best theoretical result in quantum computing in each decade? Yeah,
so I just saw that you sent me that question this morning, and I was just thinking about it in the shower because I know that whatever I answer, you know, someone will be unhappy about what I left out. But all right, to start in the 1980s. I mean, the 1980s was when, you know, the entire concept of quantum computing was first sort of clearly articulated, you know, most famously by Richard Feynman and by David Deutsch. So, you know, we could say that it's that. You know, there was not all that much in the way of non-trivial theoretical results, but there was the Deutsch-Jozsa algorithm, which was maybe the first quantum algorithm to achieve any sort of speed up over classical computing for a classical problem. It computes the exclusive OR of 2 bits with 1 query to the bits, which is not a very impressive speed up. And I think did not impress people all that much at the time, but probably it should have impressed them more, because it was a sign of how much more there was to be found. Okay, now in the 90s, that's sort of the easiest decade, because there's the choices are completely obvious there. The 90s saw the announcement of Shor's algorithm, which is really the thing that started quantum computing as a field, as opposed to just an idea being pursued by a few oddballs. So Shor's algorithm to factor integers in polynomial time, that itself built on a sequence of prior breakthroughs, that came in the year or two before it. There was also Simon's algorithm, which Shor's algorithm is a sort of adaptation of. And Simon's algorithm built on the work of Bernstein and Vazirani, which gave the first oracle problem that was solvable in quantum polynomial time, but not in classical polynomial time. So those were spectacular results, but then a very close second would have to be the discovery of quantum error correction and quantum fault tolerance. Okay, which is what convinced most of us in this field that building a scalable quantum computer should not present any fundamental problems of physics. If the laws of physics work the way that we think they do, it should be merely an unbelievably hard engineering problem, right? You don't have to perfectly isolate qubits. You only have to very, very, very well isolate them. Okay, so those were absolutely crucial discoveries that have set the agenda for this field, and I would say the quarter of a century since. Now the aughts, the 2000s, here it's a lot harder to pick one thing, because there were so many different developments that happened that sort of consolidated the revolutionary advances that there were in the 90s. But I would say that in the 2000s, people discovered remarkable quantum algorithms, often using intuitions that they had brought over from physics or from the study of quantum walks. So Andris, of course, there was your algorithm for element distinctness in n to the 2/3 time in 2003, which is still to me a very, very striking thing. There was the exponential quantum speed up via quantum walk from Childs et al. There was finally this business of game trees was fully understood, right? That the thing that that I had worked on in the 90s, and that also you had worked on, Andris. There was the remarkable quantum algorithm of Farhi, Goldstone, and Gutman for evaluating any game tree for chess or Go or any other game in the square root of the amount of of the number of nodes of the tree. Okay, so showing that you can basically achieve the full Grover speed up for these problems, and using intuitions that had come from scattering theory and in particle physics. There was a deeper understanding of the quantum adiabatic of quantum adiabatic evolution. So those were some important advances in quantum algorithms. There was also the HHL algorithm for implicitly solving systems of linear equations, and and of course there were many advances in quantum lower bounds also in that decade. But as I said, it's just very hard to pick one thing. In the 2010s, we've witnessed some spectacular solutions to some long-standing open problems. So I mean, just last year, was it last year or this year? I don't know, but we saw a proof that MIP star equals RE. In other words, that if you have two provers who cannot communicate, but who do share entanglement, and who are otherwise unlimited in their power, then even if you're only a polynomial time verifier, they can prove to you that an arbitrary Turing machine halts. Okay, that is an absolutely staggering discovery. This is the first time that I would say that quantum complexity theory has reached all the way up to sort of the cosmic realm of computability theory, okay, all the way up to the halting problem, right? The conventional wisdom is that quantum mechanics says nothing about computability. It only talks about complexity, but now it is talking about computability. You know, and this also was a major advance in pure math. It refuted this Kahn embedding conjecture in C-star algebras. We also saw just a couple of years ago, finally a solution to the problem of BQP versus the polynomial hierarchy relative to an oracle. That was by Ron Raz and Avishai Tal. That's a problem that I had cared about enormously for, you know, 20 years really, for the whole time I've been in this field. I had sort of set up a program for how to solve that problem, which Raz and Tal more or less followed. But you know, I had no idea how to complete that program, and that required a very major advance in classical circuit lower bounds. There was you know, the breakthrough by Urmila Mahadev, where she showed how any quantum computer can prove its results to a classical polynomial time skeptic, you know, using some cryptography. And by the way, you know, Urmila's breakthrough, you know, built on a sequence of earlier breakthroughs in verifiable quantum computation, right? Which one could also mention. Okay, so those to me are you know, a few of the most spectacular results of, let's say, the last 10 years, at least the theoretical ones. Yeah.
Yeah, thanks. So
Yeah.
now moving on to open problems. What are your three favorite open problems?
Oh man, it's hard. It's really hard to pick only three. But you know, I mean, we are in the happy circumstance that many problems have been solved, right, in just the last few years. But there are many that remain open. So let me just mention, you know, a few that I really like. One of them is, you know, what is the power of quantum proofs? And in particular, you know, can a quantum proof or a quantum state you give to someone to prove something, can it always be simulated by a classical proof of a comparable size? This is the question of QMA versus QCMA. And we still don't have even an oracle separation between these two classes. Okay, likewise, we don't know if two quantum proofs are more powerful than one quantum proof, right? This is the question of QMA2 versus QMA. As far as we know, QMA2 could go all the way up to non-deterministic exponential time or something crazy like that, but it could also be no more powerful than QMA. You know, even with all of the breakthroughs that we've seen in the last few years, you know, these questions have somehow been untouched. Secondly, you know, I would like to, you know, I think it's time to just finish off the questions of, you know, what is the largest possible quantum speedups, you know, in the, let's say, in the decision tree model, right? We have, you know, we've seen amazing progress just in the last few years on these questions. So like it was known, you know, when I was a student, you know, with Lav Grover first getting into the field, you know, you know, my holy text was the paper by Beals, Berman, Cleve, Mosca, and DeWolf. Quantum lower bounds by polynomials. And, you know, that paper, among other things, it shows that for any Boolean function, the classical query complexity is at most a quantum query complexity to the power 6. You know, and we've known that that 6 should not be the right answer. I believe for a long time that that 6 should really be a 2. All right, well, we now know that it's not a 2. You know, between deterministic and quantum, we know that there's a 4th power separation. I'd say the more relevant question is randomized versus quantum. there, my former student, Shalev Ben David, managed to get a power of 2.5 separation. Avishai Tal has improved that to a power of 8/3 separation. It should be at least a power of 3. In the meantime, Avishai and others have improved the 6th power relationship to a 4th power relationship. So the truth should be somewhere between 3 and 4. Okay, but one could also ask, what is the largest possible separation between quantum and classical query complexities for a partial function? And of course, Andris, you and I had a paper about this 5 years ago, but our conjecture there regarding k-fold correlation remains not completely proved. Avishai has made a big advance on it. One could ask, what's the largest quantum speedup for problems with permutation symmetry, where now we know that the answer is between cubic and quadratic. But one wants to know sort of what else is out there in the vicinity of Grover's algorithm, and is there, what might be there that does even better than Grover's algorithm? Okay. Now the third question that I'm going to pick is one that has acquired a lot of importance just very, very recently, especially with Google's achievement of quantum supremacy, with their 53-qubit superconducting device. And this problem is sort of, how do you do a quantum supremacy experiment? And there are different ways of formalizing what we mean by this, but we could say with a very small depth quantum circuit, with a sampling problem. We sort of I won't formally define it. I'll say we know a near-term quantum sampling task when we see one. So how do we do something like that, but in such a way that the answer can be efficiently verified by a classical skeptic? Okay, so I would say that the biggest drawback of the existing quantum supremacy experiments is that to verify the results requires enormous classical supercomputers, and we're inherently limited to verifying quantum computations on at most about 50 qubits. If it was with 100 qubits, then you wouldn't have the classical resources even to just check the quantum computer's results, let alone to find those results. Okay, so how do we, with a near-term device, do sampling problems where we can actually recognize, what is going on, recognize that the quantum computer is doing the right thing? Ideally, also something that would be useful for some external purpose.
Thanks. So now moving on to experimental side.
Yeah.
What are the things that you would consider the biggest achievements in quantum technology until now?
Okay. All right. Well, I would say first of all, the experimental progress, over the 20 years or so that I've been in the field has been phenomenal to watch. Right. And, a lot of people get impatient and they say, well, why aren't we there yet? It's been, 30 years, really, 40 years since Feynman, depending on when exactly you start the clock. I still can't buy a quantum computer on Amazon. What's the holdup? But I think that it's very important for people to have a sense of scale. That from Charles Babbage, in the 1830s, until the invention of the transistor, that was more than a century. Okay, more than a century between the theory and when the hardware advanced to the point to really make it truly practical. And if you look at what has happened with quantum computing hardware over the last 20, 25 years, I mean, people have gone from being barely able to control 1 qubit, not being able to do it, even a single 2-qubit gate with a reasonable fidelity, to now having much better control over systems of 50 qubits, or soon probably 100 qubits, and so on. Okay, so we are not there yet. coherence times and so on are not, and the gate fidelities are not good enough yet to really scale and do scalable fault tolerance. But they're orders of magnitude better than they were when I joined this field. Okay, and I would say mostly that has been a more or less steady progression. It's not been a matter of one or two amazing breakthroughs. It's been a matter of just the experimentalists getting steadily better and better at this stuff. Having said that, we did, of course, witness a spectacular milestone just this past fall. That was Google's announcement of quantum supremacy. Okay, and that's something that we knew was might be on the horizon. I was I would say in the faction that was urging the experimentalists to go and do this, to sort of reassure them that yes, indeed, this is interesting, to outperform a classical computer, even if it's for a problem that's completely useless in itself. And even if you don't have error correction, even if it's not scalable quantum supremacy, still, just prove the point that you can exploit the enormous dimensionality of Hilbert space, for some computational purpose, right? And that has now been done. A year ago, one could not have said that. Okay, and we should not underestimate that achievement. But the next big milestone, of course, is going to be the first demonstration of useful quantum error correction, and that has still not been done, and that is a thing that we look forward to.
Okay, and now the last question from the moderators. So what would you study if you have one PhD student? What would you study if you had 10 PhD students? And what would you study with an infinite amount of PhD students?
All right. Well, let me start with 10 PhD students, because I do have on the order of that. Well, I mean, I have 6 and I have a couple more coming, okay, in the fall. So I guess with 10 PhD students, I'd be doing mostly the same stuff that I am now. Which, I would love to tell you about the wonderful research that I'm doing. Unfortunately, since COVID happened and, the world shut down, I've been doing almost no research. I mostly, I help watch the kids, I answer my email, I deal with my blog, and then the day is over. But when I was thinking about research, I'm still thinking about the foundations of quantum supremacy experiments. I'm thinking about questions that come from quantum gravity, from the black hole information problem, from Lenny Susskind and his friends. My 6 PhD students, they all have their own projects. So, I don't really tell them what to do, okay? I mean, if they come to me asking for problems, I suggest problems, and I hope that they like one of them, right? But, they also come up with their own projects. I mostly just try to create an environment for them. I try to just help them succeed and help them find a problem that they'll be passionate about, okay? So it's not like they're my assistants or something like that, except only maybe very, very occasionally when, a student and I would find something where, the student could help me, but I mean, mostly I'm helping them, okay? If I had only one PhD student, I guess I would be doing the same, except that I would have, more time. That's all, a little bit more time. If I had 100 PhD students, then that's all that I would be doing, would be advising them. I wouldn't have time for anything else, probably not even for this Q&A session right now. But, if I had an infinite number of PhD students, then I feel like I would, solve P versus NP, solve the Riemann hypothesis, solve everything else by just asking the ith student to, examine the ith string and see whether that was a proof or not. Infinity is really a lot of students.
That was a great answer from a computer scientist. Thanks. So now we come to the questions from the people who registered here, and in the registration form they could put in some questions, and
yeah,
I will ask them, and also Andris, you will ask them. I will ask the odd question, Andris, the even questions. So now you have actually said about what you believe, how quantum computing evolved from the 80s to the 20s. But then Jonas Kmogo from South Africa asked, what can we expect in the early 30s? Does the progress in quantum computing largely depend on the ambition from Google, Microsoft, IBM, Amazon, Alibaba, Intel, and Honeywell? Or will this field progress well without such corporate interest?
okay. So first of all, the early 30s, I don't make predictions about like, especially specific narrow intervals of time that are far into the future. I have learned not to do that. I mean, if I had any ability to do that, I would not be a theoretical computer scientist. I would be Warren Buffett. Okay, I would be an investor. Okay, so one can give a lot of clarity about what are the next steps that have to happen in the development of quantum computing. Okay, fault tolerance, error correction, scaling, applications to quantum simulation. One can say what has to happen before what else. One can sort of give a directed acyclic graph. But then as for how long, each step will take, that could depend on, exactly as you asked, how interested people are, how much money are they willing to spend on it? Will someone, eat a bat or a pangolin and, start a pandemic that shuts down the entire world, including all the experimental quantum computing research, right? All sorts of bizarre hypotheticals like that. Okay, so so I don't know, but I hope that by the early 30s we will have useful quantum computers, meaning ones that are useful for learning more about condensed matter physics, learning about material science, maybe quantum gravity, maybe even chemistry, and that are programmable. And I think that is a realistic prospect. It would surprise me a lot if we already by then had like full scalable fault tolerant quantum computers. But again, it depends on how hard people want to push this. The answer to the second part of your question is absolutely yes. I mean, within just the last 5 or 6 years, what we've seen happen is that experimental quantum computing research has grown well beyond the budget of any like individual investigator at a university, right? Or I won't say beyond the academic system entirely, okay? But there are now titans in the arena, right? There's now including all of the ones you mentioned, where each one like for a Google, for a Microsoft, for an Amazon, to spend 100 million or 200 million on an experimental quantum computing effort, by their standards, that's a very small investment. That's an exploratory investment, right? By the standards of academia, that's just enormous. That's, we can't compete against that in funding, right? There is, I think there's going to remain an enormous role for academia for the foreseeable future. Already we see that the big players, when they want to know what to do with the devices that they're building, they come to us. They ask us that, and so we're still going to be thinking of new things to do with these devices, new ways of building them. But I think that the actual scaling up, it's going to, it's already past the like $100 million level. It's going to be before long at the $1 billion level. And, this requires either a large government program or else a large corporate interest if you want to make it happen.
Thanks a lot. That was a clear question.
Yeah.
So, Andris.
Yeah, so so Tim Leonard from Accenture Technology, Germany is asking, what graph problems could benefit from speed-ups of sampling algorithms?
Okay, so I mean, I know of, many quantum speed-ups for graph problems, as do you, Andris, but ones that specifically come from sampling, I'm having a hard time thinking of an example. All right, then now I'm going to do what I threatened to do before we started. Andris, what do you think? Do you know an example of a graph-related sampling problem?
I think one can speed up classical algorithms for example, volume estimation. So basically,
okay, sure. Oh yeah, and then we could call that sampling, right? Because it relies on sampling. But okay, but that's still not really related to graph theory, right? I mean, maybe I mean, we do know that quantum walks on graphs, can mix faster than classical walks, and with the exact quantum speed up depending on the graph. And so, so that's a potential area where you might get a benefit, but I don't want to, do what I often criticize in others, which is sort of rattle off potential applications without having any idea of what quantum algorithm would actually fit the bill.
I mean, Xanadu is sometimes announcing, or at least hoping for that boson sampling, or more precisely its extension is Gaussian boson sampling.
Okay, so if that's what's being asked about, then maybe I ought to address it specifically. So there were some papers from the group at Xanadu about using boson sampling to do graph isomorphism and to do find like hidden structures in graphs. I'm not convinced that they're seeing any quantum speed up there. I've looked at these papers. They all seem to depend. Some of them make claims like, well, if you could see the entire distribution, then that would reveal, information about the graph, like its isomorphism type. But that's simply irrelevant because, in boson sampling, you don't see the whole distribution. You see a single sample, or a small number of samples, and you have to reason from that. And so I'm just, look, as one of the inventors of boson sampling, nothing would make me happier than if it had an actual application,
sure,
especially to something spectacular like graph isomorphism. I'm not convinced that it does.
Thank you. So coming to the third question, you actually mentioned now in the beginning, or maybe in the first question of Andris, that actually when you went to Berkeley, you started with machine learning.
Yeah, so it turned out to be a big area. Maybe I could have stuck with that. I don't know.
Yes.
Yeah.
So we might come back to that question actually, or Andris might.
Okay.
But we have collected here a couple of questions about quantum machine learning. And I mean, let me ask them all in these three questions, and then you can answer them in any order. So
great, perfect.
Mine Ogretir from Aalto University in Finland asks, what do you think about the recent developments in quantum machine learning? So it's a general question. Laurent Quarella from Ad Infinitum, Belgium asks, could you tell what is the most challenging issue faced by quantum machine learning in its current state of progress? And Rabin Svosti from University of South Carolina asked an interesting question, because this is about using not only machine learning, but quantum machine learning for quantum computing itself. So what are your thoughts on potential use of quantum machine learning for optimizing the efficiency of quantum circuits? So I give the word to you.
Okay. All right. Yeah. So quantum machine learning, something that, by the way, 20 years ago, I proposed, to Mike Jordan that I would, that would be my PhD project, that I would somehow combine quantum computing with machine learning, which at that time was a completely crazy thing that, absolutely no one was talking about, and you know, but then I just could not figure out what to say that was, you know, non-trivial, because, you know, you can take anything and you can put the word quantum in front of it, but that doesn't mean that you actually have a speed up, or, you know, that you've actually, you know, said something new, right? Now, you know, what's happened in the last 10 years is that there's been a tremendous amount of excitement about quantum machine learning. I would say that the work has been widely varying in quality. I would say that, you know, there have been you know, really fascinating questions, you know, about, you know, where can you get a quantum speed up? There have also been claims, you know, and sort of people even founding whole companies, you know, or sort of basing whole business plans around, you know, the belief that quantum computers are going to massively speed up, you know, all sorts of machine learning problems, when, you know, the evidence just has not supported that. Okay, and you know, so I would say that the situation now is that for many machine learning problems, you know, whether that means, you know, finding a model for your data, for, you know, classification tasks, for lots of things, there will be polynomial speed ups. You know, there will be, you know, this type of speed up that comes from Grover's algorithm, or you know, from you know, quantum median estimation, and for many variants of that. And for but if you want an exponential speed up for a machine learning problem that actually matters in real life, I would say that after, you know, a decade of work in this field, it remains very unclear to me whether you're going to get that or not. Okay, there are, you know, there have been some proposals for how you might get it. You know, there was one involving Betty numbers, involving, you know, topological data analysis. There was one proposal that I really loved, you know, a very, you know, clear one by Karanidis and Prakash. This was for doing recommendation systems, like what Netflix does when it recommends movies to its users. But, you know, just making exponentially fewer queries to a data structure about the user preferences than a classical algorithm would have to make. So for several years, I gave out the problem, well, can you actually prove that that separation is for real, right? Which was something that Karanidis and Prakash had not done. Can you actually rule out that there could be a similarly efficient classical algorithm for the same task, if, you know, all you want is to, like, sample some recommendations that a user might want? So some of you might know what happened next. I had an 18-year-old undergrad by the name of Yiwen Tang, and she decided to take this as her project to prove a lower bound. She worked on it for a year, and, you know, for a year was just unable to prove this separation, kept running into obstacles. And after the year, she said to me, you know, I think the reason why I've been unable to do this is that there actually is a classical algorithm that's only polynomially slower than the quantum one. And, you know, I found that hard to believe, but I told her to keep working on it, and she was right. Okay, so Yiwen dequantized the Karanidis Prakash algorithm, which had been, I would say, the clearest example that we had of an exponential quantum speedup for machine learning. And now, building on Yiwen's breakthrough, by now a whole bunch of other quantum machine learning algorithms have also been dequantized, or as I sometimes call it, Yiwenized. Okay, so this actually brings us right to the second question. The most challenging issue facing quantum machine learning is clear. It's to find some exponential quantum speedup for some machine learning task that, you know, is not completely contrived, you know, so that kind of matters in real life, and, you know, where there's like an actually sensible model of how you get in the input and how you measure your state to get out the output, okay? And that resists Yiwenization, okay? That resists, you know, being dequantized for similar reasons as the recommendation system's algorithm was. Okay, so I don't regard the answer as obvious, but sort of the fate of, do you get huge quantum gains for machine learning? That should be viewed very, very much as still an open research problem. Okay, in fact, I could have picked it as one of my 3 problems earlier. Okay, and now as for using quantum machine learning to optimize quantum circuits, well, I mean, as I said, maybe the first step would be to show that quantum machine learning sort of helps for anything, right? There's also a little bit of a chicken and egg problem here, right? That if we could use quantum machine learning, then, we would already have useful quantum computers, right? And, so, I've seen some ironic examples like this where, some of the problems, there are some number theory problems that arise when you're trying to build, very small quantum circuits from certain sets of gates. And these number theory problems can, in some cases, be reduced to factoring, meaning that if you had a quantum computer, then it could help you for designing a quantum computer, right? So, there are some funny chicken and egg problems like that. But I mean, look, once we have quantum computers, we expect that the Grover speed up will help for all sorts of things, eventually, including, one would imagine, designing the next generation of quantum computers. Just like right now we use classical computers to, lay out the circuitry for the next generation of classical computers.
Thanks. So the next question is, what do you think about topological quantum computing from Mohammed Sameh, Cairo University?
Yeah, well, I hope it succeeds. I mean, I'm in a very good position as a theorist of being able to cheer every approach to building a quantum computer while, needing to pledge myself to none of them, right? So I talk to, the superconducting qubit people, I talk to the ion trap people, I talk to the neutral atom people, I talk to the photonics people, and I talk to the topological quantum computing people, like, the ones at Microsoft, for example. And I wish all of them the best. Now, topological quantum computing is the one that, you could regard as sort of very, speculative or ambitious, even by the standards of building a quantum computer, right? Because, with superconducting qubits, we now have, as I said, programmable systems with, 50 or so qubits that, are not yet where we need them to be, but, you can already do impressive things with them. With topological quantum computing, the current situation is we have 0 topological qubits. Okay, not even one has been demonstrated, and this has not been for lack of trying. This has been, apparently it is just really, really hard to do these experiments. There have been for a few years, reports of, what looks like the detection of Majorana fermions, which would be a first step in the right direction. Even then, it's not like a direct confirmation that the Majorana fermions were created. I read that just very, very recently, there was a, like within the last week or two, there was a claim to have, detected other non-abelian anyons. Did anyone else here see that? Andris, Zoltan, Ronald, did you see that?
Yes.
Yes. Yeah. So, okay. So that was just within the last week or two. So maybe we should give that time to, be evaluated. But, the bottom line is that to build a topological quantum computer, you need to make a new state of matter, which has never been seen on Earth. Okay. Which has these excitations that behave neither as fermions nor as bosons, but in this more complicated way. And then you have to control them. You have to braid them around each other. So, so why even do it? Well, I would say that there is a very strong argument for pursuing it, which is that it is, if it worked, then it would massively reduce the need for active quantum error correction. Okay, and if you look at the history of computing, then it might give you a strong indication that would ultimately be the right way forward. Because in the 1950s, von Neumann worked out the whole theory of error correction and fault tolerance for classical computers. So how do you build a reliable classical computer out of noisy vacuum tubes, noisy electromechanical relays? Okay, and he theoretically solved that problem, and his solution ended up being mostly set aside and not used, because then transistors became practical, and they were just so good. I mean, if you look at the set of all of the transistors that are in your computer, all the billions of them, there's maybe one failure per year on average, and that when a cosmic ray hits it. Okay, so transistors, you could say, are just naturally fault tolerant. They're sort of fault tolerant for physics reasons as opposed to computer science reasons. And and you could say, well, then shouldn't we find the quantum computing analog of the transistor, right? I mean, ironically, to invent the transistor itself, already required quantum mechanics. But I mean, I mean the qubit version of the transistor, like a building block of a quantum computer that's just so naturally protected from decoherence that you don't even need to do all of this hierarchical error correction on top of it. So we don't yet know what that would be. Topological quantum computing is the closest thing that we have to that. And so that alone is reason enough to pursue it. So, I hope that it succeeds. In the meantime, another thing that's happened is that ideas from topological quantum computing, get sort of stolen, they get ripped off, and they get applied to the more conventional types of quantum computing, with the most famous example of that being Kitaev surface code.
Thanks a lot.
Mm-hmm.
And now we also collected a bunch of questions that was about another type of architecture, not gate type of quantum computing, but adiabatic quantum computation, which is sometimes called or sometimes differentiated from called quantum annealing, and,
Mm-hmm.
and also the company that is claiming to do that, Drawback. And let me summarize those questions.
Mm-hmm.
The first two questions was about, maybe the first I could even read. Do you think adiabatic quantum computing is still a viable path towards further proving quantum supremacy? Here I'm thinking of the new quantum annealer made by Drawback, which increases the number of qubits and connections. This is Pegasus, I guess.
Mm-hmm.
But I'm also thinking of general universal adiabatic quantum computing. And the second question by Jamie Gill from UWM is similar. The threshold for quantum supremacy is pretty straightforward, 53 qubits. I'm not, yeah, okay. This is for, I guess, gate models and universal quantum computation. Is there any such comparable thresholds for quantum annealers like D-Wave, or will there always be classically simulable?
Mm-hmm.
And finally, a very similar question by Thomas Schips, which asks, what are the theoretical and empirical results we have on quantum annealing, quantum adiabatic?
Okay, so all right, so I think we should separate out two different things. First is sort of the theoretical algorithm, right? The adiabatic algorithm, as a way to solve optimization problems or other problems. And and this is a hardware independent thing, right? This is an algorithm that could be run on an annealing device like D-Waves, if the temperature were low enough and so forth. But it could also be run on a conventional quantum computer. Okay, but even if you had a completely perfect quantum computer to run the quantum adiabatic algorithm, we still don't know kind of what speed up it would get over the best classical algorithms for problems that really matter in real life. I would say that has been a big research area in quantum computing theory for, a little over 20 years now. Okay, and it remains an open research area, I would say. We have learned some important things about it. Okay, we know that there are situations where the adiabatic algorithm can reach a global minimum exponentially faster than specific classical algorithms, such as simulated annealing. And just very recently, just earlier this year, there was a breakthrough result by Matt Hastings, where he has shown the first example of a black box problem where quantum annealing, reaches the global optimum in polynomial time, but any classical algorithm provably requires more than polynomial time, more than a polynomial number of queries. It's not yet an exponential number. It's like n to the log n queries. Okay, but even just to prove this took a lot of really deep ideas. All that I can take credit for is having urged Matt to work on that problem. On the negative side, there's also some very, very interesting recent work by Elizabeth Crossan, where she has given evidence sort of against the adiabatic algorithm, giving speed ups over classical algorithms for like a variety of situations that you might care about in real life. Okay, and this is most of this is not, I mean, Hastings' result was rigorous, right? Elizabeth's result, work is mostly, let's say, at a physics level, right? It is, it's at the level of physical intuitions. But I think that, it's, once again, it's clear that with the adiabatic algorithm, we can get Grover's speed ups, when they're there to be had. We hope that there will be some cases that actually matter in real life where the adiabatic algorithm would give us bigger speed ups, ideally even exponential speed ups. The hard part is, well, you got to compare against any classical algorithm, right? That means simulated annealing. That means quantum Monte Carlo. It means, classical algorithms that are sort of specifically designed to try to simulate quantum algorithms. Okay, that means classical algorithms that know about the structure of the class of problems that we're picking. So I think that, just like with quantum machine learning, that still has to be considered an open research area, and I don't care how many people say otherwise or say that, we're basing our whole company on the belief, on the established fact that, quantum adiabatic evolution gets this huge speed up. Like, sorry, no, it's not, if we're talking about speed ups that matter in real life, then that's not an established fact. Okay, it is an open question. Now, regarding D-Wave in particular, like, man, I've heard so little about them, for the last few years. I mean, they, when, earlier in my career, D-Wave was kind of, the biggest game in town in terms of companies that were, doing quantum computing or selling, I guess from maybe 2007 to 2012 or thereabouts, they were maybe the only game in town, right? The only company that was saying, we are building quantum computers and you can buy them, which made a lot of people excited. My blog, I guess, sort of rose to prominence mostly just by me saying, like, this stuff that D-Wave is saying, like, a lot of it, we don't know how to evaluate. Some of the stuff that we can evaluate, we know that it's not true, right? And I was saying things that I think were very, very pretty uncontroversial within the quantum computing community, within the research community, and yet sort of came as a revelation to the journalists and to the business community that was sort of not hearing this, that was hearing, a sort of filtered story that did not reflect the consensus of the research community. Okay, so, now since then, I mean, D-Wave has changed as a company. They've actually, like, ironically, as their hardware has gotten better, they've also scaled back the claims that they've made, right? And, so they do have devices now with some thousands of qubits. And, they can do annealing, I think that they're interesting as a physics platform. I am not convinced that we have a clear example of quantum supremacy with these devices. I mean, and the trouble is, just so people understand, the qubits that D-Wave is using, are, they have, I would say, about 1,000th or a 10,000th of the coherence time of the superconducting qubits that Google is using, let's say, for its supremacy experiment, which are otherwise very similar qubits, right? So I mean, D-Wave sort of optimized for trying to get as many qubits as they could, as quickly as they could, with very good interconnections, but not worrying, nearly enough, I don't think, about what is the actual coherence of the qubits. How much do they behave as qubits? And, and at the time people were saying, well, okay, but, you're all just sitting around and talking about it, and they're going ahead and doing that. So, okay. And we said, okay, fine. So, one can do it, one can try it, but we just, we don't see how you're going to get a quantum speed up that way. And I would say that so far the results look pretty consistent with that. Now it's possible that they will eventually have, convincing demonstrations of quantum speedups. I mean, I fear that it will be a little bit like, the boy who cried wolf, right? That, like if you've made, like X number of claims in the past that turned out to be wildly exaggerated, then even if you do eventually make a claim that, that holds up, like, are people going to have the energy to track down each one, right? I mean, I feel like a lot of the interest, has shifted now. Ironically, the interest did not shift away from D-Wave because of any of my blogging, right? As far as I could see, that had zero effect on, making people less interested in everything that D-Wave was saying. What made people less interested was that Google came along, and IBM and Rigetti and all of these others, and then all of these people who, I just, maybe like, if you imagine people like turning their heads to like the shiny thing, well, now there's a different shiny thing, and they turn their heads to that one.
Thanks a lot. That was a complete answer. So we are actually running out of time slightly. So I would propose that actually from this section, we only ask 2 more questions. I ask one, and then that's the last one. And then we go to other sections and shortly just continue. So I would actually ask question number 13 from Zeki.
Can you scroll down for that?
This is Zeki Seskir, who is actually a member of Q Turkey and also a very good member of QWorld, a very competent member. And he asks the following interesting question. What are some of the expectations that quantum computing will probably fail that will make government agencies, venture capital to stop reduce investing in this field? Do you see a quantum winter along the way to fully realize universal quantum computer of reasonable size? Say 5,000 qubits or even more.
Yeah. I think that a quantum winter is absolutely a possibility. I mean, if you look at the history of AI, it would be foolish to, deny that a quantum winter is a possibility, right? I mean, AI has now been through, I guess, either 2 or 3 winters, depending on how you count, as the sort of cycle of hype went up and down, right? One of the reasons why I've been so concerned, for the past, 13 or 14 years to try to counter, irresponsible quantum computing hype on my blog is that, you do have to, maintain your credibility as a research field, right? And if you are telling people that, we are confident that we're going to get huge quantum speedups for machine learning problems in, 5 years, and then that doesn't happen, then, okay, I mean, maybe, look, I mean, given who's the president of the US, I mean, maybe we're now in a post-accountability world where, nothing matters anymore and no one will ever be held to account for anything. But, I personally, I feel like, maybe we will be held to account for saying things that are, making confident predictions that just don't come true. And so this is one reason why, I will sometimes make guesses about the future, but I try to be conservative. I feel like we should underpromise and overdeliver. And if people get the idea that there are going to be these massive applications to business that are going to repay the investments that people are that companies are making in it, and that furthermore those applications are going to come soon, then they may be setting themselves up for a huge disappointment. Okay, and I think that it's very, very important to tell people that. Whenever I talk to business people about the subject, I try to convey that message very clearly, so that if there is a winter, and if they're people have their pitchforks out and they're looking for someone to blame, I can say, well, look, I told you, look, it's right here on my blog, it wasn't my fault. So, these things, are entirely possible, and then of course, the history of AI also teaches us that even if there is a winter, it's possible that winter doesn't last forever. It's possible that, after winter comes a spring.
Sure.
Yeah.
Thanks. So let me jump to question 18.
Okay.
So, Rishi Sridhar from Sweden is asking, if you would start your quantum journey all over again from when you were 25 years old, I guess this should be corrected to 20 years old or 18 years old. How would you go about it?
Yeah. I guess my fine. Okay, I guess my quantum journey, it did start when I was about 17 or 18, but I could start the clock when I was 25, which would have been, let's say, in 2006 or so. I mean, maybe the first thing that I would do would be I would write, I would publish a proof of of the sensitivity conjecture. I would publish the proof of a super quadratic separation between randomized and quantum query complexity. I would publish all the stuff that I now know, and that would impress. I would buy up Bitcoin. That's the other thing. Okay. I would maybe somehow try to warn people about Trump. I don't know. I mean, it's very, it's very hard to rewind, the clock. I mean, I guess the supposition is that we go back in time, and I don't know the specific things that I know now, but I know some kind of general wisdom about life or something like that. Because otherwise I would presumably just do the same things all over again, because I would be the same person. The trouble with this is that I'm not sure that I really am that much wiser than I was when I was 25. I wish that I could say that I was, but I mean, I know more about, having kids and having a family. I know about having students and, managing a research group. But, in terms of quantum computing, I'm not really sure that or let's say in terms of strategies and research, I don't really know if I have more wisdom. So maybe I would have just done the same things.
Thank you. So we also have a few questions which I will just summarize, because connecting to career advice and literature and so on, usually the questions are the following. If I want to get into quantum computing, should I study physics, mathematics, or computer science? Or if I'm a physicist, computer scientist, mechanical engineer, how can I go on towards quantum computing? Which path should I follow? This is a very usual question which you got from many people.
Sure. I mean, the question of which path to follow, that very much depends on you and your interests, right? I mean, quantum computing is a polyglot field. It is it's like if quantum computing was a country, it would be either Yugoslavia, Pakistan, the US. It would be that kind of country, you know, made up of immigrants from, you know, or from physics, from CS, from, you know, some from math, from electrical engineering, some even from chemistry, from philosophy. Okay, so you know, but I would say that you know the main feeders into this field, you know, the two biggest ones are definitely CS and physics, and you know I think that the duality between those two has always been central to the field, and it remains so, right? And so you know this field is going to continue to have strong presence from both. I think that numerically there are more physicists, you know, more people in this field from a physics background than there are from a CS background. Certainly, if you count the experimentalists, you know, then there's many more. I like to think that we in CS also make a crucial contribution, you know, to making this field what it is. You know, one could also double major, right? But you know, as I said, it depends on you. Right? Are you, you know, it depends on things like, are you interested in, you know, helping to actually build quantum computers? Well, then, you know, maybe physics or electrical engineering. Are you interested in thinking about quantum algorithms? Then maybe CS. Are you interested in thinking about in ruling out quantum algorithms? Well, then definitely CS, right? You know, if you want to do something as useless as that. Okay, you know, as quantum complexity theory and lower bounds. Are you interested in quantum error correction or quantum programming languages? Well, you know, those things are a little bit more on the interface between the hardware layer and the software layer, and those you could really do either. But also you can try it. Like, you know, for me, it took a few semesters of physics as an undergrad to realize, like, I am really not good at differential equations. Right? I am just really not very good at, you know, at continuous math. I mean, especially PDEs, right? And, you know, I like things, you know, clear and discrete. And so that sort of pushed me into, you know, CS and discrete math. And then, you know, I learned about quantum computing, and that was kind of a side door by which to get back into physics, you know, which is something that's always fascinated me. So, but it depends on you, right? You know, take some of the courses and, you know, try to do some research with some faculty and see what you like more.
Thanks a lot. So about the literature, we chose actually two questions. One is from Maxim Dimitriev from University of Latvia, who is actually a member of QWorld, who asks, besides this complexity zoo, which he likes very much, which paper or book would you recommend that summarizes the current knowledge about quantum complexity classes?
John Watrous has a very nice survey article about quantum complexity theory, although it's already 10 or 11 years old. Besides that, the main thing that I would recommend is lecture notes of courses. So I have lecture notes from a course that I taught in 2008 that you can find on my homepage. Umesh Vazirani, who was my and also Andris's advisor at Berkeley, has an excellent set of lecture notes. Andris, do you have lecture notes on the web?
No, I don't.
Oh. Wait, Ronald, do you have lecture notes?
I do, they're on the archive.
Oh, all right, good. All right, so look at Ronald's lecture notes then. And yeah, those are, I don't think that there is a textbook specifically for quantum complexity theory. I've thought about writing one sometimes, but you know, it's a textbook is something that I'd be happy to have written, but you know, but that I less so want to write. So, you know, that could be a good, you know, but I mean, part of the other problem with writing a textbook is that, like, by the time it's really time to write a textbook, it probably means that the field has died, right? Like, while the field is still developing, then any textbook you could possibly write is going to be obsolete within a few years, right? So, you know, so that's one reason why lecture notes might be the main place to go. But, you know, it would also depend on what you're interested in. Like, is it, are you interested in QMA? Are you interested in QIP and BQP/QPoly? And depending on the answer, I might point you to different places. I have lecture notes from a course that I taught in Barbados 4 years ago. If you just Google like Aaronson Barbados, you'll find those notes. And they cover a lot of quantum complexity theory, as well as the connections to quantum money and the connections to quantum gravity and the black hole information problem. So they kind of tell the story, in a slightly unusual way. But you could look at those as well.
Thank you. And the final question from this part is about online resources. Actually, online resources from you. QWorld
Yes.
has been now very open about this online education. So the question is, do you, is the 22nd question. Do you teach
Yes.
any quantum computing courses in edX or Coursera? It's from
Okay,
Arium.
well, so I don't think that it's edX or Coursera, but as it happens, I will be teaching an online course, Introduction to Quantum Information Science. I will be teaching it through UT Austin's online computer science master's program, and I will be doing that starting 1 month from now. Okay, so because of COVID, I'll be lecturing like I am now anyway. I'll be lecturing on Zoom, and and UT Austin now has an online master's program in CS, and I will be participating in that using what's normally my undergrad. It's an advanced undergraduate course, Intro to Quantum Information Science. Covers everything from the only prerequisites are like linear algebra and some classical CS, and then it does the basics of quantum mechanics through quantum teleportation, quantum cryptography, Grover's algorithm, Shor's algorithm, the adiabatic algorithm, all kinds of stuff like that.
Thanks a lot. And before
I should add, by the way, I also have lecture notes for that course. Those you can find on my blog or on my homepage. Okay, and if you Google Aaronson lecture notes, then I think you'll find those. Okay.
And before moving to the last section, somebody, actually Vijendra from the Australian National University, didn't put a question, but says that please pass the message that I read. His PhD dissertation thesis done under Umesh Vazirani in 2014, and I thoroughly enjoyed it. Possibly the best PhD thesis I've read so far. Enjoyed his complexity jokes. So that's a good.
Thank you. You inspire me to put more dumb jokes in my future papers.
And we go to the last section. We only chose, actually, because of shortness of time, two. I think we have updated it. Okay, it's somehow not updated, but we chose two questions, but I can, yes, from the audience. I would ask the first question, and then I leave Andris to the second question. And the first question is actually from Karim El-Shafti that we chose, about variational quantum circuits in general, I would ask, but his particular question was, how can we use variational quantum circuits to reduce the size of huge classical neural networks? For example, if we have a hybrid paradigm. I would actually ask in a more general sense, this has been going on, this variational quantum circuits for now. What do you think about them? Do you think
I have no idea. Okay. Answer. This is the first question that is just completely I draw a blank. I don't know if I also read some stuff about VQE, for example, variational quantum eigensolver, and these are heuristics where I have yet to see sort of a clear theoretical analysis that tells me what kind of speed up are you going to get, which it's not to say that there isn't a speed up. It's just that I think that there is a vacuum of sort of theory that really directly addresses the main point, and whether you can use that to optimize the sizes of neural networks. I have no idea. And
along the same line, what do you think about QAOA, like the quantum?
So QAOA, okay, that is an algorithm that we do know something about, and you know, basically every application of the QAOA that has, you know, ever been proposed, you know, has been killed. Okay, people should understand clearly that that is the current situation, right? And you know, I'm not even sure that Farhi, who was the inventor of the QAOA, would disagree with that assessment. Okay, it was invented, you know, and I was there at MIT when, you know, Eddie was working on it. It was invented as a quantum algorithm for trying to solve unique games. Okay, you know, it didn't work for that, but then they said that, well, it can get a better approximation for this planar, you know, a certain special kind of planar SAT problem, you know, than the best known classical algorithm gets. You know, I was very excited about that. I blogged about that because I said, you know, this is the first time that we've seen a quantum algorithm that actually gets a better approximation ratio than any known classical algorithm does for an NP-hard optimization problem. Then my blog post inspired about 10 classical computer scientists to write a paper that said that they can not only match, but they can beat that approximation ratio via a classical algorithm. Okay. Since then, you know, there have been other proposals for how you might use the QAOA that I think, you know, have also turned out not to give a speed up over what we can do classically. Okay. The best that one can say in terms of advantage of the QAOA is there was a paper by Aram Harrow and Ed Farhi, which says that you know, you can use QAOA to sort of do a sampling-based quantum supremacy experiment. Okay, so in other words, you can use it to sample distributions that could not be efficiently sampled classically, at least exactly, unless the polynomial hierarchy collapses. So this is, you know, you could sort of understand that as saying, like, we can't prove that the QAOA ever solves any problem better, but at least the classical algorithm cannot easily reproduce its exact pattern of failures. Okay, that's sort of what that's saying. Now, I think, you know, it is possible that the QAOA will get a speed up for something. You know, just like with machine learning, just like with the adiabatic algorithm, it is a research topic that people should keep working on. It's an interesting algorithm. It's a natural algorithm, but, and you know, people just keep, you know, founding companies, you know, based on the QAOA, right? Writing grant proposals, you know, give us $20 million to find, you know, to study practical applications of the QAOA, you know, writing papers, you know, about the QAOA, right? Just understand this algorithm has not been established to ever get any clear quantum speed up for anything, you know, that could possibly be practically important. And, you know, on the contrary, you know, the applications, you know, that were put forward have been dequantized. Okay, and people keep talking about it as if it's not the case. Or, you know, like when you know, it's been weird for me, right, that I've been to so many talks about QAOA, and then, you know, they will just not even address the question that, are you getting a speed up over a classical algorithm or not? And then if I explicitly ask that, then they'll just sort of talk around it and say, oh, we don't want to talk about that, and then just go back to that, right? But, you know, that's the entire point. There is no point in building a quantum computer if you're not getting a speed up over the best classical algorithm. And so I think that, you know, as we continue to study the QAOA, we should have that in mind and not lose sight of what the whole point of this field is.
Thanks. And
yeah,
the final question is, what do you think about quantum cryptography and post-quantum cryptography? Do we need
well,
only on the former?
Yeah, those are two very different subjects, you know, despite having an edit distance of only one syllable from each other, I guess. I mean, quantum cryptography is an absolutely beautiful theoretical idea. You know, I love teaching it in my undergrad class. It's just a remarkable information theoretic protocol. And I think that it remains totally unclear whether it will have real world application, right? Beyond maybe some very, very tiny niches. I mean, there have been quantum cryptography startups like ID Quantique and Magic. They have not done particularly well, okay? They've been around for a while now, but what they found is pretty much the only customers for quantum cryptography, at least right now, are a few banks and government agencies that mostly just want to test quantum cryptography, right? And the biggest problem, I think that if public key crypto had happened not to exist or to have not been discovered, then QKD would have been completely revolutionary, right? It could have changed the world. But QKD arrived into a world where public key crypto already existed and was already is used all across the internet, and so it is solving a problem you needing extremely special hardware with a limitation on distance if you're using fiber optics, or needing complicated quantum repeaters that look almost as hard to build as a quantum computer, or needing communication to and from a satellite, which the Chinese government demonstrated a few years ago. And that was a remarkable achievement, but it only works when the weather is good and the bit rate is really bad. So totally unclear how to make it practical. And if you did spend the enormous effort to make it practical, well, you're solving a problem that is already solved very, very conveniently and well by conventional public key cryptography. Okay. And now that actually brings us to the second part of the question, right? Which is, some people have joked that, well, one of the biggest applications for a quantum computer will be to create the market for quantum cryptography, right? And it will do that by breaking, all of our existing cryptography. I mean, I think people were already making that joke 25 years ago, right? But the trouble is, well, there is also post-quantum cryptography, okay? And so there are classical public key crypto systems that we do not know how to break even with quantum computers. And I think that that has become a field in its own right, and that field is now in a pretty good shape. I mean, there are some very good candidates for post-quantum classical crypto systems, quantum resistant crypto systems. The most famous are the ones based on lattices and the so-called learning with errors, or LWE problem. There are others, based on isogenies of elliptic curves and other problems. So these codes are, many of them are theoretically very nice. They even let you do things that our existing public key codes would not do, like fully homomorphic encryption, doing arbitrary computations on encrypted data without ever decrypting it. Until recently, people would say about these quantum resistant crypto systems that, well, they might be nice in theory, but they're just too impractical because the key sizes are too large. The message, the blow up in the message size is too large. I think that has been ameliorated a lot recently, and these systems are actually either practical already or they're well on the way to real world practicality. And, Google and others have even done real world demos of them, right? I mean, and an important point to keep in mind is that you really only need public key cryptography to do key agreement, right? And once you've agreed on a secret key, then from then on, you can use private key cryptography. And for private key cryptography, even with a quantum computer, we expect that the best that an attacker is going to get will be the Grover speedup. So I think that we actually are in a pretty good situation for, like we have the candidates for post-quantum crypto systems. The hard part, is just going to be to migrate everybody to those systems, right? So in the US, the NIST, the National Institute of Standards and Technology, is having a competition to create standards for post-quantum crypto. That process is already underway. But even once they've agreed on a standard, then it could easily take a decade or more for people to actually switch to these things. I mean, when you go out into the real world and look at security, see that like there are people who are still using web browsers, that were hackable back in the 90s, right? Just because they haven't upgraded them, right? So, I mean, there's a huge lag between, solving a security problem in principle and actually solving it in practice. But I think that we do know how to secure electronic commerce and secure the internet, most likely even in a world with quantum computers.
Thank you very much, and thank you for time and
Sure.
questions. Maybe Abu should say some closing words.
Sure, sure.
Thank you very much. We still have more than 100 people. They are watching us. Also, thanks to them.
Well, thank you, everyone, for listening.
We still had some questions, but unfortunately, it's still 100 minutes, 10 minutes than we promised. We will still some time from the Scott. Thanks to Zoltan. Thanks again to Agnieszka. Thanks to Andris. And yes, Scott, thank you very much.
Thanks so much for inviting me. It was a lot of fun.
Yeah, people asking second session, but I think it will be too much.
Well, Andris, Ronald, go corral one of them into the next session. All right.
Okay.
I already did one, Scott.
Oh, you already did one. All right. Oh, okay.
Time to Andris now.
All right.
Okay. Thank you very much, everyone.
Sure. Absolutely. Absolutely. All right. Good to see you. And those of you in Europe, good evening. I'm going to go have lunch and play with my kids now. All right. See you guys.
See you.
Bye.